Thank you. Thank you for letting me know.
No problem.
Yeah, I usually pause the recording right at the very beginning to make sure that no students get caught on screen because I post them online and we're under legal obligation not to post students. But I forgot to start it again. And thank you. If I ever do that again, if you'll let me know again, hopefully I won't. So for those of you watching the recording again, a set of vectors v1 through vp in Rn is said to be linearly independent if given these scalars. This equation implies that all the c's must be 0. So notice what we've done here. We've taken a linear combination of of v1 through vp. We've taken a multiple of v1, a multiple of v2, a multiple all the way up to vp, and added them all up. And we got the 0 vector. Now, if I set c1 equal to 0, then this multiple is the 0 vector. And if I set c2 equals 0, if I set them all equal to 0, if I set all the c's equal to 0, this will definitely be true. What I'm saying here is if that's the only way to get the 0 vector, if the only way to get the 0 vector is by setting all these scalars, all these numbers equal to 0, then the set of vectors is linearly independent. If there are others, it's not linearly independent. So note, setting C1, C2, all the way up to CP, let me put equal signs there. Setting all of those equal to 0 will definitely make, let me call this equation star. Will definitely make star true. If the only way star can be true is with the c's all 0, then set v1, v2, all the way to vp is linearly independent. Let me give you some examples to get a feel for what's going on here. Let's say v1 equals the vector 1, 2, 3, and v2 is the vector 2, 4, 6. And we'll just consider the set of these two vectors. Now, certainly, I hope I can erase this now. Certainly, if I put a constant of 0 in front of v1 and a constant of 0 in front of v2, I get the 0 vector. So 0 times 1, 2, 3 plus 0 times 2, 4, 6 is 0, 0, 0 plus 0, 0, 0. I don't mean to insult your intelligence here, but 0 times 1, 2, 3 is just 0, 0, 0. And 0 times 2, 4, 6 is 0, 0, 0. And if you add these two vectors up, you get 0, 0, 0. So certainly, as always, by putting zeros in front of all the vectors, I do get the 0 vector. But can you think of other numbers I could put in front of here and here such that I get the 0 vector? Can you think of a number I could put here and a number I could put here, not both of which are 0, at least one of them can't be 0, such that if I did the multiplication and then added them up, I would get the 0 vector?
If you put 1 and minus 1/2.
Yeah, that would work. 1 and minus 1/2 would work just fine. So 1 times 1, 2, 3 plus minus 1/2 times 2, 4, 6 gives me 1 times 1, 2, 3 is just 1, 2, 3. And minus 1/2 times 2 is -1. Minus 1/2 times 4 is -2. And minus 1/2 times 6 is -3. And if I add these two vectors up, I end up with 0 plus 0, 0, 0. I get the 0 vector again. There's the 0 vector, and here's the 0 vector up here. So even though 0, 0 worked, it wasn't the only set of numbers that worked. So there are other pairs of numbers here besides 0, 0, which give me the 0 vector. So these two vectors, so there are C's, not all 0, that make C1 times V1 plus C2 times V2 equal to 0 in this particular case, where V1 is 1, 2, 3, and V2 is 2, 4, 6. You just chose C1 equals 1 and C2 equals minus 1/2. So these vectors are not linearly independent. They're not linearly independent because there's at least one more way of doing it. And once there's one more way of doing it, there's infinitely many more ways of doing it. Instead of using 1 and minus 1/2, I could have used 2 and 1. I could have used, sorry, 2 and minus 1, I should say. I could have used minus 2 and plus 1. There's infinitely many ways of doing this. But the point is there's at least one other than using all zeros. Is everybody okay with this? So whereas, let's say I gave you the following two vectors. So here's another example. Let's say V1 equals 1, 2, 3, and V2 equals, oh, let's keep it relatively simple. How about 0, 1, 0? Now, certainly, if I took C1 times V1 plus C2 times V2 and set it equal to 0, the 0 vector, certainly C1 and if C1 and C2 are both 0, this is true. this equality is true. The question is, are there other solutions? If there are, they're not linearly independent. And if this is the only one, then they are linearly independent. So, are there other solutions? Let's try to find out. We know techniques to find out what all the solutions of this are. We can go ahead and write this vector equation in other forms. We could go ahead and write it as a system of linear equations. We could go ahead and write it as a matrix equation. But our go-to, our favorite, when we're trying to actually do computations, is to write it as a augmented matrix. So I can go ahead and write this as an augmented matrix. So 1, 2, 3 in the first column, 0, 1, 0. Vertical bar, 0, 0, 0. Let's see if there are any other solutions. So this thing is almost in, it's almost in reduced echelon form already. There really isn't too much more to do. So I can go ahead and leave the first row alone, 1, 0, vertical bar 0. I'll take row 2 and subtract off 2 times row 1, leaving me with 0, 1, 0. I'll take row 3 and subtract off 3 times row 1, leaving me with 0, 0, 0. That wasn't very hard. I happen to pick nice vectors. Picking the v2 equals 0, 1, 0 really helped. But let's rewrite this now in echelon form, or as a system of linear equations. So this says 1 times, usually I call it 1 times x1, but this time my variables are c1 and c2. So that first equation says 1 times c1 plus 0 times c2. In other words, 1 times c1 equals 0. And that second row says 1 times C2 equals 0. So this says C1 and C2 are both 0. These are the only solutions. So the answer to this question, are there other solutions, is no. So in this case, V1 and V2 are linearly independent. We write linearly independent so often, we tend to abbreviate it LI. And from what we did here, we can see an easy way, or not easy necessarily, but a way using a technique we already know to be able to determine whether a set of vectors is linearly independent or not. What we wish to determine whether the set of vectors, so in this case I just gave you 2, but let's say I give you more, perhaps more, V1, V2, all the way up to VP, and each of these vectors is in, let's say, Rn. We want to determine whether these vectors is linearly independent. I hope you don't mind if I use the abbreviation that I already introduced, Li, linearly independent. A lot less writing. just write the augmented matrix. Where the first column is V1, the second column is V2, all the way up to VP. What I only had two columns over here because I only had two vectors. Vertical bar, then the zero vector. And row reduce to see if zero is the only solution.
What does it say? So it can right there. Yeah, what does that say?
So if we wish, right here?
Yeah.
Yeah, sorry. So if we wish to determine, okay, I'm gonna stop and let you catch up.
What's after determine?
If we wish to determine whether the set of vectors, sorry, I'm getting excited, so my handwriting is getting worse. This is definitely an exciting point. So in row reduce, to see if only solutions is C1 equals C2 equals everything equals 0. And you know how to do that? You don't even have to find the solutions. If there are no free variables, then that's the only solution. So if there are no free variables, if you have a pivot position in every column, then this is the only solution. If there are free variables, so if there's at least one column without a pivot position, then there are other solutions. So this one's the linearly independent one. This one's not linearly independent. So you already know the machinery to determine whether a set of vectors is linearly independent or not. Just write it as the columns of an augmented matrix, row reduce, until you can tell whether there are free variables or not. So let me give you a definition. Set of vectors that are not linearly independent the abbreviation again, is said to be linearly dependent. If you want, you can abbreviate this one LD. Let's see if we can start to get some idea of what linear independence means sort of visually, intuitively, so it doesn't just degenerate into algebraic nonsense. A set of one vector is linearly independent. Say is Li, as long as the vector is not the zero vector. If it is the zero vector, you can put anything in front of it and multiply it by whatever number you want, and you still have zero. A set of two vectors is Li. So that first example I gave you that turned out not to be linearly independent, remember when I gave you 1, 2, 3, and 2, 4, 6? Why wasn't that set linearly independent? What was special about those two vectors, 1, 2, 3, and 2, 4, 6? Graphically speaking, if you were just going to draw them as arrows.
They were the same.
Well,
Just
they're not
scaled,
the same.
yeah, it's scaled differently on the same line.
Yeah, they're on the same line. They're parallel, right? 2, 4, 6 is just 2 times 1, 2, 3. Does that make sense? So a set of two vectors is linearly independent as long as they're not parallel. If they're parallel, you can always take a multiple of 1 to make the second one, and then add -1 times the second one. And that gets you back to the zero vector. Basically, being parallel means that you can always, take a multiple of 1 to get the other. How do you feel about that? Is that okay? Awesome.
What does the set of one vector v as Li do?
So the set of a set of one vector v is linearly independent as long as the vector is not the zero vector. As long as the vector isn't the zero vector. The zero vector by itself is already linearly dependent. And any set containing a zero vector is linearly dependent. It's not linearly independent. As long as if there's a zero vector in there, it's automatically not linearly independent. So a set of two vectors is linearly independent as long as they're not parallel. The zero vector is parallel to anything. It's just 0 times anything. A set of 3 vectors ask you to make a hypothesis here, is linearly independent as long as they're not what? If two vectors are linearly independent as long as they're not parallel, what do you suppose would make, what do you suppose has to be true or not true for three vectors to be linearly independent? Just by analogy. Not parallel this time.
Coplanar.
Coplanar, right? As long as they're not, they don't all lie in the same plane. So if I gave you three vectors which were coplanar, they wouldn't be linearly independent. And if I give you three vectors which are not coplanar, they are linearly independent. So for instance, R is, let's say, 1, 0, 1, and B2 equal 1, 1, 0. Oh, and B3 equal, space here, B3 equal 2, 1, 1. Three vectors here altogether. Linearly independent. Is this a linearly independent set?
What's the second number in V2?
In V2, 1, 1, 0. 1, 1, 0. And V3 is 2, 1, 1. So, oh yeah, it's a little hard to see. Sorry about that. So are these linearly independent? Now, we could just go ahead and write this as the columns of a augmented matrix, put our 0, 0, 0 down on one side of the other side of the vertical bar. But I think in this case, we might be able to eyeball it. Can you see any special relationship between V1, V2, and V3? Can you describe V3 for me easily in terms of V1 and V2?
It's the sum of
Yeah.
V1 and V2.
V1 plus V2.
Yeah, right. V3 is equal to V1 plus V2. If you add this and this, you get that. Well, that's just another way of saying, let me just subtract V3 from both sides. So I get V1 plus V2 minus V3 equals 0, equals a 0 vector, just by subtracting V3 from both sides and turning the equation around. And what I just wrote is that 1 times V1 plus 1 times V2 plus -1 times V3 equals a 0 vector. And so there are other solutions. I have other things I can put in front of the V1, the V2, and the V3 that aren't all zeros. They give me the 0 vector when I do up my linear combination. So these three are definitely not linearly independent. But we can also picture this. We can also picture this graphically. So if I take a look at the vector 1, 0, 1, I come out 1 on my x1 axis and go up 1 on my z axis, or my x3 axis. And so I have that vector right there. There's v1. And I also have the vector v2, which is 1 on my x-axis, 1 on my x1 axis, and 1 on my x2 axis. So there's v2. But I also have the vector, which is 2 on my x1 axis, 1 on my x2 axis, and 1 on my x3 axis. So out 1, no, so out 2, and up 1, and over 1. So I have my v3. And the thing is, all 3 of these vectors lie in the same plane. So all 3 vectors, v1, v2, v3, lie in the same plane. And as it turns out, v3 is just the sum of v1 and v2. So of course it lies in the same plane as v1 and v2. Because using v1 and v2, I can only get to the plane which contains v1 and v2. So we have I guess we'd call it a theorem. I'll call it a proposition. I don't want to make it as big as a theorem. Your book calls it theorem number 7. A set of vectors. They probably talk about vectors in Rn. No, they don't. Set of vectors. Is linearly dependent if and only if at least one of the vectors can be written as a linear combination of the other vectors. If at least one of the vectors can be written as a linear combination of the other vectors. So in our last example, we could write v3 as a linear combination of v1 and v2. So in our previous example, rewrote V3 as a linear combination of V1 and V2. This was the observation we made, that V3 was just the sum of the first two vectors. We could have also written V1 as a linear combination of V2 and V3 just by rearranging this. So V1 equals V3 plus -1 V2. All I did is get V1 by itself. Or I could have written V2 as a linear combination of V1 and V3. So if there's at least one of the vectors that you can write as a linear combination of the others, the vectors are linearly dependent. Let me underline dependent. And let me write down another theorem, which hopefully will be, the proof will be obvious to you. This one I think I will call a theorem. If V1, V2, all the way up to VP are vectors in Rn, where P is greater than N, where P is greater than N. So in other words, we have more vectors than the dimension in the space. Yep. So this is the if part. Here comes the then part. Here comes the conclusion. So we have a hypothesis. If we have more vectors than we have dimensions in the space, then the vectors are automatically, I'm going to put the word automatically in, even though that's not really a very formal word. Linearly dependent. You have more vectors than you have than the dimension of the space here. The vectors are automatically linearly dependent. Let's take a look at the proof. If we write the matrix, where the first column is V1, and the second column is V2, all the way up to the pth column, which is VP, vertical bar, then the zero vector. So if we write that matrix, then the number of columns is P. But each of these V's is an Rn. So the number of rows is N.
What does that say under the matrix?
What's that?
What does that say? Under the yeah.
It says P columns.
Oh, okay.
and you have n rows. Since we said that P is greater than n, this matrix has more columns than it has rows. We can't have more than n pivot positions. N is the smaller of the two numbers. So there can't be a pivot position in every column. So they're free variables. We already know if there's free variables, these vectors, these column vectors are linearly dependent. Because there are other solutions besides the zero vector, besides the zero solution. And at the very end of the proof, to indicate that the proof is over, we put a filled-in square. Very satisfying to put that filled-in square there. Proof done. Got it all copied down? So if we're in R3 and I gave you one vector, that's the set of one vector might be linearly independent. It might be linearly independent. If I gave you the zero vector, it's linearly dependent. If it's not the zero vector, it's linearly independent. If I gave you two vectors, they might be linearly independent. They might not be. If they're parallel, they're not linearly independent. They're dependent. But if they're not parallel, they're linearly independent. If I gave you three vectors, they might be linearly independent or they might not be, depending on whether or not they're coplanar. But if I give you four vectors in R3, they are definitely linearly dependent. If I gave you five vectors, they're definitely linearly dependent as long as we're in R3. How much time do I have? Okay, I have another analogy for you, but I only have 1 minute. So I'll save my analogy for the beginning of Wednesday's class. Are there any questions at all? All right. Some of you I'll see in like 5 minutes. Some of you I will see on Wednesday. Bye now.